So, Mikhail Belkin he's a professor at Halisiolu, I think. Anybody here speak Turkish?
I think
You
it's
know how to pronounce it?
Heligiolo.
Pardon me?
Heligiolo, I think.
Jolo. Okay, very good. Data Institute, which is at the University of California, San Diego, and an Amazon scholar. His research is on theory and applications of machine learning and data analysis. His recent work has concerned understanding remarkable statistical phenomena observed in deep learning. I hope Joshua is somewhere in the background. One of the key recent findings is the double descent risk curve that extends the textbook U-shaped bias variance trade-off curve. I can't pretend, Misha, I'm technical enough to know what that curve is, that extends the textbook that extends the bias variance curve beyond the point of interpolation. Misha is an ACM fellow and recipient of a NSF Career Award and a number of Best Paper and other awards. He's editor-in-chief of the SIAM Journal on Mathematics of Data Science. And enough of my babbling. This is Mikhail Belkin.
Thank you very much, and thank you for the invitation. Really great to be here, albeit virtually. I will talk about today. I would like to talk about some, maybe more mathematical aspects of dimensionality and feature learning in deep learning, and particularly LLMs. The majority of the talk will not be about LLM specifically, but I'm going to discuss LLMs and at least some aspects of what makes them their success to be so surprising, and really came as a complete surprise to so many of us. I think let me start by saying that why is it? Sorry. Oh, it's okay. I mean, we have witnessed clearly what is an unbelievable progress of artificial intelligence just in the last few years. Many tasks which we thought were completely out of reach of machine learning systems just like maybe 3 or 4 years ago are now being solved very successfully. Things like the bar exam, interview questions, even like International Math Olympiad problems. It's really quite remarkable and stunning. And what we're seeing is that mathematics is really transforming the world. With large language models and other deep learning systems are nothing else but mathematical formulas. And, despite them being like relatively simple, although they have very large matrices, but it's basically a bunch of matrix multiplications and nonlinearities. And despite them being like, somewhat simple, we do not understand how, why, or when they work. This is a sort of, I think, an unprecedented state of affairs. And I have argued recently that if we want to have any chance of controlling or understanding the systems, we really have to understand the theory of AI. And what I'm going to talk about today is maybe like a small step towards such a theory. And I wrote like a kind of opinion piece of why we need theory in sort of mitigating AI risk, among other things, but also just sort of controlling and understanding the systems. In any case, let's think about what is surprising about this model. And first, let me just make a couple of comments about this. The first comment is that I think mainstream belief has long being that human-level AI was in principle possible. I mean, going back to probably people like Turing and von Neumann and so on. Now, what is really surprising and unexpected is the nature of the current models. And the fact is that these LLMs are relatively simple statistics models and trained on limited data. And let me expand on this a little bit. So first, what I mean by simple statistical models, let's just consider a sort of LLM type of model. What do you have? You have tokens, which we can just think of them as words. And the sort of the structure of the LLM, I'm ignoring the internal structure for now, but just that LLM itself is a probability distribution on the next token given the context. So if your context is 4,000 tokens, for example, then you're simply computing probability of the 4,001st token given those 4,000. And once you compute this probability, you sample from this and you shift the window, the context window by one, and you just keep doing this. Now, this is done one token at a time, right? So you're always predicting the next token. And furthermore, these models, when we train these models, they're trained autoregressively, meaning that they're trained to predict the next token, given the sort of the previous, well, in this case, 4,000 tokens. Now, this is actually a very basic thing, and this is what's known as a Markov chain. And the only difference from this and classical Markov chains, which you know have been considered for like 100 years or so, is the size of the context, right? The context is much, much larger size. 4,000 is actually not that big. Now we have like even context of a size 1,000,000, you know, even larger. So now let me maybe take a step back and sort of look at a little bit of, tiny little bit of history. And there was a sort of a famous quote from Chomsky, who in 1969 says that the notion of probability of a sentence is an entirely useless one under any known interpretation of this term. And well, frankly, this is a rather extreme view to say that probability is completely useless. A sort of, I think, a very mainstream view was more recently expressed by Peter Norvig. And basically, he said that was about 12 years ago. Markov model of probabilities cannot model all of language. We need to have some sort of nested probabilistic models that, you know, cover words, syntax, semantics, and so on. And this, I think this was a very, like, in my opinion, this was a very mainstream view, and I would have personally agreed with this, like, at that time. Well, there is a big but. LLMs are, in fact, Markov models. So this, I think, was a huge surprise, that Markov model could, in fact, do something so remarkable. Just predicting the next token is enough. You don't need to have any sort of complicated search, multi-level modeling, and so on. Whatever happens inside of these models can be expressed as predicting a single token. Now, I have to say that Peter Norvig changed his view, and he basically says now that artificial intelligence is, AGI is already here. And again, I would personally agree with his view at this point. So 12 years later. So that very radical shift, right? And there was a sort of old you know, commonplace in AI, saying that you know, building statistical models like this, like Markov chains, to obtain intelligence is like climbing a tree to reach the moon, right? When you climb a tree, you get higher, but presumably you cannot reach the moon no matter how tall the tree is. And this is Dali's representation of that concept. And what it seems that actually that's exactly what happened. We climbed the tree and indeed we reached the moon, right? Like these models clearly have competence which is extremely high and comparable to or exceeding human competence in many tasks. Now, let me point out that there are actually these models. I will discuss dimensionality in a minute, but let me first point out that these models also have surprisingly few parameters. And let me just make a couple of points about this. Right now, largest LLMs have about a trillion of the order, well, the ones we know about in any case, have about 1 trillion weights. Now, if you compare this to biological systems, which is perhaps an unwarranted comparison, but you know, like this is probably the best we can do if we want to have some sort of comparison to biology. You can think of weights being equivalent to synapses, and 10 to the 12 is actually a very small brain. It's a mouse brain. So in contrast, the human brain is about 100 times larger and of the order of 10 to the 14 synapses. So even though the largest LLM is, in terms of the count, again, I'm emphasizing this is not a proper comparison, is equivalent to something like a mouse, its ability in terms of language far exceeds abilities of any human. For example, it just it knows, say, GPT-4, whatever model you take, it like knows on the order of 100 languages, which is probably far beyond what any single human can hope to know. So the biological anchors seem to be greatly overestimate the number of parameters, and there was like a work a few years ago, basically this idea of forecasting the power of AI based on this biology, but it looks like biology needs many more synapses than these systems. And now you can say, of course, in the human brain, well, there are a lot of synapses which are not related to language, but language is a big chunk of a human brain. Definitely not 1/100th of a brain is related to language. In any case, let me sort of go back and like discuss the puzzle of dimensionality specifically and what is so strange about this. So to say very generally, the world is we're faced in the world with stimuli of very high dimension. We have images, we have speech, we have language. These are all very high dimensional phenomena, and really few phenomena low dimensional. And even those low dimensional things like measurement, maybe you go to a doctor and I don't know, your blood pressure or something, right? That's a low dimensional thing. But even they come as a time series. So effectively, they're high dimensional. And there is a key question: how do we make sense of high dimensional world, given that intrinsically high dimensional spaces are not explorable? And when I say not explorable, there is a precise mathematical sense in which they cannot be understood. And a sort of classical view on this is that the curse of dimensionality is a very serious thing, and we must carefully manage dimensionality of our method. And it seems that in modern practice, dimensionality, you can sort of just ignore it. Just assume things will work, and indeed they work. So let me now sort of give like one example in terms of the LLMs, how high dimension the things are. So consider a model, which is, let's say, something like GPT 3.5 or something like that, that has roughly 4,000 context length, and the vocabulary size of the number of different tokens is about 50,000. So now, remember, so for every context, we need to predict a probability of the next token. So you can think of it as a matrix. On one side of the matrix are all possible contexts, and on the other side of the matrix, you know, on the x-axis, so to say, there are probabilities for each token. Well, how big is this matrix? Well, the matrix is the number of all possible contexts times the vocabulary size. How many contexts do you have? Well, you have 4,000 context lengths. And each context length, you can have one of the 50,000 tokens. So you have 5 times 10 to the 4 to the power of 4,000. That's one side of the matrix, and the other side is 50,000. Now, needless to say, this is a gigantic number, and no process in the universe can, you know, feel the you know, can feel this. There is just like no way to even, this is more than the number of particles in the universe and so on. On the other hand, the training size of this matrix, the training size which we use to fill this matrix is about 1 trillion data points. So we think we have a lot of data, right? That's like all of the data on the internet, but that's just 1 trillion data points. It is not even a drop in the bucket, not even a drop in the ocean compared to the number of all possible configurations that you may have. So this is a real mystery if in this case. Oh, I see there is a question. Is the dimension the number of words? Well, the dimension is the number of, yeah, so the yeah, so there are a couple of good comments. So dimension is the number, so what I'm counting here is the number of all possible sequences, so the number of all possible completions. And I see Gary makes a point that dimensional language is not a sequence of random words, and language lives in a low dimensional manifold. This is, of course, exactly true, and this is what I'm going to discuss. But notice that just saying that it's not a number of, so this is, of course, counting like all sequences of words. And most of the sequences are completely nonsensical, right? Because you're just like stringing together random words. But even if you just count the number of sensible sentences of length 4,000, this is far too large, because imagine that for every position you have at least 2 possible completions. So at the very least, this would be something like 2 to the 4,000. And 2 to the 4,000 power is still bigger than the number of particles in the universe. So just that doesn't help. So no matter how you count it, the dimension of the thing is gigantic. So what do we do with this? Oops, why is it not? Sorry. So this is the problem of dimensionality, and let me sort of rewrite it in a slightly more mathematical, sort of reformulate it in a slightly different way. Yeah, another point I would like to make sort of with respect to the comments is that I'm not identifying, so I'm not considering the number of synapses right now anyway. I'm just looking at the possible completions. We'll get to that later. Okay, so in general, if you have a d-dimensional space, we need e to the d points to explore it. Because, well, if you have a system with a d degrees of freedom, so what do I mean by that? If you have d degrees of freedom, you need at least 2 data points per degree of freedom. So you need something like 2 to the d data points. What does it mean? Well, LLMs are trained on something like 1 trillion data points. And, well, if you have 1 trillion data points and you need e to the d points to you know, explore a d-dimensional space, therefore the dimension of languages or whatever it is in LLMs, right? presumably they learn languages, and clearly they can speak languages quite well, is of the order of log of 10 to the 12, which is about 30. So even though like on the surface, this looks like an extremely high dimensional system, but fundamentally it seems that the dimension cannot exceed 30 because otherwise no data in the world would be enough. So the underlying data in subsisting representation must have low intrinsic complexity. And now we have all these questions. Well, what is the latent space? What is the 30-dimensional space? How do neural networks reduce dimensionality, and can we use some sort of feature in other models? And I'm going to discuss this in a somewhat simpler version than full LLMs, although I will mention the LLMs toward the end. So to summarize, it looks like language is actually a low-dimensional, low-complex problem. And importantly, only a few directions in that gigantic space of alternances are relevant for prediction. So you can kind of think, well, even though there are like many potential sentences, but to predict the next talk is a much simpler problem than what we sort of would expect. Is this okay? The sound?
Yeah, it's jumping, but I think I think it's all right. Okay, go ahead, please.
It's all right?
Yes,
okay.
Go ahead.
So let me start with a kind of very basic question. And the question is like, why can we predict anything? And well, let's just think about a very simple problem. And suppose you have one-dimensional data, and I have some data points. So this is my x-axis, and I have some data points, okay? And you may think, okay, well, something like this is a reasonable curve to fit to this data. But why is this good, right? Like, why do we think this curve is reasonable? And the answer to this is that, of course, there are potentially infinitely many ways to fit a curve to this data. But what we sort of expect is that nearby points will have similar values. So we don't expect this curve to like jump between these points tremendously. And this reflects actually something that we know about the physical space, right? If you have some sensors in a physical space, then nearby sensors should report similar measurements. And you can call it smoothness inductive bias. This smoothness inductive bias comes from physics. Most physical processes don't jump between nearby points. It can happen, but it's not typical. What does it mean? That means that basically once we impose this kind of structure, we have effectively a low dimensionality control over this curve, right? Because we know we're only considering those curves which well, first fit the data, and second, don't jump between points which are nearby. And I thought somebody raised hand. Question?
I don't see this. I don't see that raised hand here. Continue unless they really do raise it.
Milad
yes.
Nazari?
Yeah. Go ahead, Nazari. Go ahead and ask your question. Where is this? Oh, there's two raised hands. Milad, go ahead and talk. And I'll do the other one as well. Milad, go ahead and talk. You should be able to speak.
Hi, sorry, it was just a mistake.
Okay.
Oh, okay.
Let's see if the other one is a mistake. What was the other name? Yeah, let's say that we ask people to defer the oral question to the end unless it's really nuclear. Go ahead, Misha.
Okay. I'll continue then. So basically that's the idea, is that because we have the strong inductive bias based on physical proactivity in the real space, we can reduce dimensionality from having the space of all possible curves, which would be some sort of crazy space, to curves which don't drastically jump, and that's a much, much more constrained space. And once you impose this, you have very nice mathematical and practical algorithm for that, including things like kernel machines, which I'll discuss in a minute, and things like splines. Now, you can add invariance to this, for example, parallel transport, and you can say, well, you know, like, if you look at different objects, right? If you shift a little bit with respect to that object should still stay the same. So you can kind of add this to the to the to this constraint and say, well, yeah, it has to be smooth, but you also allow some change of coordinate system, for example, shifts, and it leads you to ideas like convolutional filters. Right? Because you kind of run them across your image. So basically, my point here is that low dimensionality comes from inductive biases based on physics. And what is very strange is that we don't have anything like that for language or for these more complicated things that we're dealing with. And the question is, I think, is like, what is physical law of language? Okay, now let me continue, and I'll sort of make a very simple suggestion of what something like that can be, which probably doesn't cover like all of language, but covers something at least. And just to set it up, what is the problem here? We want to learn from data. What is my data? We have xi's, which are features in some high dimensional space. And we have yi's, which are responses or labels. And I'm just assuming that they're real, but they can be, you know, like multiple things. And X is a feature space. R is this sort of response. And I have a hypothesis space which corresponds to, say, neural networks of a certain architecture. And what do I want? I want to, given this data, I want to find a function which will predict future data on xi. So it will predict yi's on xi's, which I haven't yet seen. And sort of traditionally, how did we deal with this? Well, if you think about sort of traditional practice, you have this feature space and you have a model space. What did we do for the feature space? Well, we had dimensionality reduction methods such as principal components analysis, multidimensional scaling, that's a linear, and more recently, manifold learning and, you know, like various non-linear dimensionality reduction techniques, something I worked on in particular. On the model space side, traditionally, we have ideas such as sparsity, saying that, okay, well, you write your function in some basis, and that needs to be sparse in that basis, and maybe controlling the number of parameters or the norm of parameters. So controlling the number of parameters, for example, the size of a neural network is like one of the most standard suggestions. Now, in modern practice, it's very interesting because first we have very high ambient dimension. We have non-linear structures. It's clear linear is not enough. And that's on the feature size. On the model size, we have very large parameter spaces. Okay, well, in the trillions of parameters now. And we basically do little or no norm control and little, you know, we just like more or less feed the data as well as we can and let it be. So modern practice is extremely permissive, and it looks like, you know, you don't need to control anything. Things just work out on their own, which again is very puzzling. It's very, very counterintuitive to, you know, those of us who studied sort of classical machine learning or statistics. Now, for the dimensionality reduction point of view, you know, like the sort of very standard methods which have been widely used and really have been extremely influential in both vision and language, but things like eigenphases and like lighting semantic indexing, when basically you project your data on the slow dimensional data, on the slow dimensional representation linear, and that work very well. In the nonlinear case, we had like isomap, locally linear embedding Laplacian eigenmaps, and so on, also kind of had the same idea. And what we now see is that none of these methods are good enough. And what sort of these methods, what's common among them is that they're all unsupervised. And now we see that whatever we do, it better be supervised. We have to have some sort of target in mind when we're doing dimensionality reduction. Now, from the number of parameters point of view, so remember there was like kind of on one side the data and on the other side the model in that slide I had before. The key observation recently made was that performance basically depends on scale. And scale, sort of in the most basic form, contains of three things. It's a number of model parameters, number of data, and the amount of compute. Of course, the things are related, right? Because for more parameters and more data, you need more compute. So parameters and data are sort of independent, but the compute depends on both. Well, if you think that the number of parameters is important, well, why not just take the number of parameters to be very large, potentially infinite? Okay, and why just don't take n to be infinity when n is the number of parameters? And indeed, what we have seen both empirically and theoretically recently is that the infinite number of parameters can be optimal or close to optimal. And in particular, some work we have done on double descent shows that on the x-axis here, I have the number of parameters, and on the y-axis, I have performance. So low is better. It's you can think of it as some sort of loss or risk. Basically, taking the number of parameters to be infinite is essentially optimal in many regimes. Well, when I say optimal, I have to be a little bit careful. It really depends on the setting. But I think the upshot is that I think the upshot is that like infinity is generally, well, very large number is generally very good. Oh, I see that there was a question in chat. Do you consider auto-regression to be supervised? Yes, I consider auto-regression to be supervised. This is the trick. This is the amazing trick. Every unsupervised problem is kind of becomes supervised if you pose it correctly. That's a remarkable, I think, finding, because we used to think that we have to do stuff in unsupervised ways, and then like the realization has been that you can turn all this unsupervised problem in supervised problem. And this is true for auto-regression. This is also true for things like diffusion models and vision. You basically diffuse, you add noise and then you regress back to the original image. Okay, so now this suggests that maybe infinite networks are good, right? Because if the large number of parameters is good. And actually, infinite network is something that we have known before. This is not a new idea. Actually, just like a lot of the things, right? Like auto-regression is not new. Markov chains, of course, are quite old. A lot of the things existed before, but they somehow, like, we never understood that they were so powerful, and we never saw that potential until like literally like last 5-10 years. So there is this old history of infinite networks, and going from reproducing clonal Hilbert space, which was like a purely theoretical thing, to splines in the 70s and 80s, then kernel machines in the 90s, and very recently, like last 5 years, it has been found that wide neural networks also are essentially the same thing. And here I'm sort of making a caveat that I'm saying under certain initialization conditions. And it turns out that this initialization condition is actually quite important. And this is not a full, so one has to be very careful when saying like, okay, this is an infinite network like a kernel machine. But I'll get back to it shortly. Okay, so now let me just give you a very brief reminder of what kernel machines are. If you're not familiar with this, I'll have like one-line summary of that. Basically, what you want to feed data. So this is my loss function, f of xi minus yi. Well, I'm just taking the square loss. You can take another loss. Plus some sort of penalty, making that the function doesn't wiggle too much. So that's my physical kind of proximity thing. I want my function to be nice, don't change. And in general, this is an optimization problem, all functions. So this is an impossible or very difficult problem. But there is a key algorithmic insight, is that for certain classes of the spaces, there is actually an explicit solution to, there is an explicit solution to this optimization problem. And the explicit solution is very nice. It's just a sum over all of my data points, kernels at that data point. And what do I mean by kernel? You can just think of something like Gaussian. So it's just a sum of Gaussian or Laplace kernel, which is like a Gaussian without a square. And now this sum is only over the data points. So my infinite dimensional problem initially gets reduced to a problem of optimization whose size is a number of data points. It's a very elegant thing. And furthermore, if you have the square loss, you can find those coefficients by doing a single matrix equation. So everything becomes very algorithmically tractable. And indeed, in this certain limit, wide neural networks are simply those things. And I'm not going to discuss it, but you can construct a kernel out of neural network. And as you take the widths to be infinite, you just get a solution of exactly the same form, which is extremely satisfactory. I was very happy to see that work myself because it like connected all the things very nicely. Unfortunately, that's not the whole story. And this regime, it turns out, misses a key point. And what is this key point now? And this is kind of the same thing. Well, what is special about neural networks? And well, one thing which is special about neural network is that it looks like neural network have no issue with high input dimension, while those methods that I discussed before do have an issue with high input dimension. And the question is, well, why does it happen? And here is the answer, or here is part of the answer, I should say, is that neural networks learn relevant directions. And what they do is some form of task-relevant dimensionality reduction. I am going to now give some very specific examples to give an idea of what this dimensionality reduction is. So I like it. I think this is very important to have specific examples because it's kind of like almost like physics. We need to do an experiment and we need to see what happens. Okay, in any case, here is a very simple experiment. I choose X, so X is my feature, and I take it to be a random point sampled from a normal distribution in a 100-dimensional space. So it's a pretty high dimensional thing. It has 100 dimensions. And now I'm going to take Y to be a very simple function of X. I take the first 5 coordinates, sum them up, multiply by the next 5 coordinates. Okay, so this is a polynomial of degree 2, and it only depends on the first 10 coordinates. But actually, if you think about it, it only depends on the sum, on the linear function of the first 5 coordinates and another linear function of the next 5 coordinates. So this is what's known as an index 2 model. Now, I'm going to try a Laplace kernel on this, and I'm going to try a neural network on this. And what do I observe? The R squared of a Laplace kernel is 0.25. So remember, R squared is like the square loss, but it's rescaled slightly different. So basically 1 is good and 0 is bad. And what you see is that neural network performs just much, much better than the kernel. Okay, it just destroys the kernel completely. And this, of course, is a, kind of puzzling in view of what I said before, that neural network is like a kernel, but clearly it's not like a kernel. It works much better. And I think one surprising thing about this is that how recent this observation is. Like first experiment of this type is like just maybe 5 or 6 years ago. Even though this could have easily been done like 20, 30, whatever years ago, there is nothing special here. You just need to run a neural network on like 4,000 training points. Even fewer probably would be enough. And now there is some recent work which is, trying to understand this. Okay, so what is going on? Like, why is this different from neural networks and Laplace kernels? And let me sort of give you maybe some sort of mental picture for this. And the mental picture is that neural networks are learning filters. So if you can learn the correct filter for the thing, as we will very soon see, it becomes a much easier problem. So what is a neural network? Well, neural network is the following, right? You have some input, which is a high dimensional, well, 100-dimensional space in that case. And then you have the next layer of a neural network, and you have some sort of matrix W1 which you obtain by training this neural network. Now, if you think about W1 transpose W1, it's going to be a 100 by 100 matrix, right? Because if my W1 is like 100 times D, then W1 transpose W1 is going to be 100 by 100. And you can kind of think of it as a transformation of this 100-dimensional space. I'm taking square root for some sort of normalization. It doesn't really matter so much. So you can kind of think of a trained, and by the neural network here, I just mean MLP, by the way. This is, in some sense, the simplest neural network. So think of a trained MLP as some sort of filter, which is low rank. And what do I mean by low rank? That effectively does some sort of dimensionality reduction. And then it's followed by some nonlinear thing, and that thing could be a kernel machine. Okay, so that's now I have to bring in like one mathematical object here in addition to this, and this is the following. This is the average gradient outer product, and it's basically, how do you think about this task relevant features? And this is applicable to any function, not just a neural network in principle, like any model, you can just take F. So what is this? I take F, for every training data point, I take gradient of F with respect to the input, not with respect to the weight, but with respect to the input. I don't care about the weights here at all. And I take the outer product of the gradient, which is a matrix. Now, this matrix essentially tells me the following. It tells me that which input directions affect response for model F. So imagine I'm changing my input a little bit. If that change doesn't affect my response, I can kind of ignore that change completely, and I just can ignore this direction, right? So if in this direction, if I change my X in this direction, and the output doesn't change, then what do I care about this direction? So the hope is that this AGOP matrix is low rank, and only a few directions affect the output of the model. so that's basically the idea. And I should point out, this is not a new, this is not a new object. This object existed for like also like something like 30 years or so, has been used for that long. So another way to think about it, if you take the top eigenvectors of this matrix of AGOP, they basically tell you the main directions of change. So it's sort of like principal component analysis, right? The principal components give you the direction of the large variance, but that is unsupervised. The same thing, but supervised. So the top eigendirections, eigenvectors of AGOP give you most important directions with respect to the output of the model. Okay, so that's basically what it is. Okay, I have a sort of more mathematical slide, but maybe I'll skip this one. So now let's discuss why is neural net better. So remember, I have this neural net and I have this index model. Now I have W1 transpose W for the train network. And I'm going to compare this to the AGOP of this model. And what you can see is that these two matrices are actually very similar. They're not quite the same, but they look almost the same. And now let's see what happens. So imagine now I train my neural network, and then I discard everything about this neural networks except for these two matrices. One matrix is W1 transpose W1, and the other matrix is this AGOP. Okay, so I forgot that I trained the matrix, I just kept this. I kind of extracted these two matrices from the trained neural network. Now let's look what happens that I'm going to train another set of some other classifiers, and I'm going to only use these two matrices as the sort of filters for the data. So now if I use NFM as a filter, you can see I can train a kernel machine or a neural network on just 500 training samples as opposed to 4,000 for the initial one. And I do it actually very well. With AGOP, it's even better. Same thing, but even better. And we can maybe skip the P10. If I don't do any filtering at all, both methods effectively fail. So maybe one way to think about this is that if you train a neural network, this is what you extract from the neural network. Okay. Okay. Now, let me maybe just give you an example, and this is what happens when you train a neural network. So this is a very simple task, just like whether the person in an image wears glasses, okay? So there are a bunch of like celebrity images, and the task is to identify glasses. And if you look at this W1 transition, so that's basically what happens. Okay, so now let me now I can formulate what we call the deep neural feature ansatz. With that, oh, and this is joint work with Parthe Pandit, and we we claim, so ansatz means a kind of like a guiding principle. It's like a proposal. It's not a mathematical theorem. It's something that is a useful way to think about this object. That this W1 transpose W1 is the same as AGOP. And sort of you it visually, they're quite similar. So when I say same, I mean that they're very highly correlated. I don't mean that literally. And you can do this for deep networks. Test the correlation in the two matrices, and you can see that this correlation is not 1, but it is quite high. It's like 0.9 something. And this is true for MLPs. This is true for convolutional neural networks. This is true for transformers, for RNNs. And so as far as we know, this is seems to be the general principle for most architectures. Okay. So now we can kind of identify those two things, the structure of the weight matrices and some other sort of mathematical object. And we claim that this is how neural networks, or at least MLP, presumably like all of them, do dimensionality reduction, or at least it's part of how dimensionality reduction. For MLPs, that's all they do, but for other things, it's less clear. And let me sort of give you some confirmation that this works. And you can think, well, can we learn from neural network? Okay, this is great, but what can we do? And it turns out that if you raise idea and transform into, sorry, not transformers, into kernels, they do perform very well. In fact, they, in many cases, outperform MLPs. Now, what do you do? Well, remember, I kind of claim neural networks is some sort of dimensionality reduction based on relevant features, plus a nonlinear printer machine. And I'll just go quickly. You can build what we call a recursive feature machine. So you build a kernel predictor, extract that matrix from the filter your data with this, and you plug it back and retrain your. So it's a recursive procedure and arguably continuous indirect way through optimization. There are network issues. Is that okay? Can you hear me?
Yes, there have been some network issues. I'm standing here just to be able to interrupt you and ask you to repeat something if it was cut out by the network.
Okay, great. Yeah, please do. If I'm cut off, I'm happy to repeat, of course.
Okay. Go ahead.
Okay. So that's basically a recursive feature machine. In that, so what it does, it builds a predictor, then extracts its dimensionality reduction, and then repeats filters the data and repeats this process. And the expectation is that every time it does better, because it's somehow extracting this low dimensional representation. Now, this is a specific way with a Laplace kernel, but let me show you an example of this, which I think is quite interesting. And this is what you may call grokking. It's related to something which was called grokking in neural networks, but it's not for modular arithmetic. It's a different problem. So the problem here is actually quite simple. These are two classes from CFAR 10. And one class is trucks, the other is planes, but we kind of cheat. We add like a little star there, and the color of that star indicates which class it is. So if you know to pay attention to that little, like few pixels in the corner, you would be able to do 100%. It's a very easy problem, but of course you don't. And here is what happens with a neural network. As you train the neural network, after 80 epochs, your training accuracy is already almost 100%, but your test accuracy is still kind of bad. It's only like 75% or so. And as you keep training, the training accuracy really doesn't improve. Well, it cannot go above 100%, right? That's the best you can hope for. But the test accuracy just keeps improving and improving, which is very weird because, like, if you think about it, why should it improve? And the reason it improves is that there is as you're training, it identifies this low dimensional subspace corresponding to these few pixels in the corner better and better, and you can kind of see the star sort of emerges. So after like another 80 epochs, you get like close to 100% performance. So the key here is that not that it's the training here is actually what it's doing. The interesting part of what it's doing is not improving training accuracy. It's actually finding that low dimensional subspace. Now you can play the same game as RFM, and you can see that after zero, like first round, you get 55%. It's terrible. The prediction accuracy is just awful. But you already identify the star very well. And after like the next iteration, it jumps to 95%, and then you go to 100%. So that's the feature learning. That's how it reduces dimensionality. And yeah, so that basically shows that this dimensionality reduction process in neural networks is very distinct from just fitting training data. And loss is really not a training loss is not a proxy for accuracy at all. Okay, so finally, well, this RFM actually works very well on tabular data. It's state of the art. Let me maybe I'll show a couple of interesting examples. Actually, let me just show, since this is about LLMs, let me show an example with LLMs. So what you can do with LLMs and other architectures is the following. You can extract these matrices, take their top eigenvectors, and then you can look at what these eigenvectors correspond to. And this is actually turns out to be very informative. So this is a transformer. This is a GPT-2 trained on tiny stories. If you take the top two eigenvectors of, if you take the top, I forget, like the top 20, I think, tokens from projecting onto singular vectors of this AGOP matrix, you can see that you have very nice semantic patterns. And you see like food and cooking and adjective and so on. And indeed, you can actually even like color code the text based on the semantic categories. And you can see that, like names is one category, and then, things like food and so on. So we definitely extracting important semantic features from, these texts. Okay, I'm sort of running out of time, so maybe I have a couple of slides of some concluding thoughts, and I'm then happy to discuss and answer any questions. So let me, first, I think the clear message here is that data are far, far more predictable than we thought, and the number of relevant dimensions is very small. Just, like we think of language being extremely rich, but it looks like it's far less rich than we thought. It's perhaps shocking discovery. I consider it to be one of the great scientific discovery, probably of all time. It's certainly was extremely surprising for a lot of us. The sort of other side of this is that predicting next talking is sufficient for human level language mastery. It looks very likely that it's sufficient for other things as well, like certain image tasks and so on. So a lot of, it seems like a lot of problems may be either solved or kind of like close to solved by just that very simple trick. All data, yeah, so going back to this, all data now are labeled data. Basically, we want to have only supervised. So we want to turn any unsupervised task into a supervised task. And doing this very systematically has yielded like fantastic results. Neural network clearly implement task-dependent dimensionality reduction. I think this is sort of not arguable anymore. current methods have been developed by trial and error, and they're kind of I can talk about it, but it's like will take longer. They're kind of a result of an evolutionary process, and I think there is really no reason to think they're optimal, and better architecture should, and I'm sure will be available. From a practical point of view, I think our algorithm, the recursive feature machine, provide both practical and theoretical framework for thinking about this. And indeed, you can sort of study many interesting aspects of deep learning, like such as grokking, neural collapse, and other things within that framework. I feel from a scientific point of view, we have to treat the things a lot like physics. We have to do experiments, and we need some sort of precise measurements to guide theory. We cannot really prove theorems. Proving theorems is too inefficient. And you know, physicists don't sort of normally prove theorems. We really need to model this classical physical approach to make progress. Not necessarily physical methods, not necessarily their specific tools, but their general approach. And I think another thing is that our understanding turned out to be far shallower than we thought. You know, we thought we understood statistics, and it looks like, yeah, you know, this in a sense has been the greatest progress in statistics. Right? You take the statistical things, and it goes far beyond what, you know, we thought was possible with statistics. And maybe I'll finish with this kind of like little tribute to Turing. This is Turing fish. So Turing, in his paper Computing Machinery Intelligence, when he you know, proposed the Turing test, he actually suggested that you need probably about 1 billion bits of memory to model human, to play the game, the imitation game, which is the basis for the Turing test. And 1 billion bits would be roughly equivalent to a brain of a fish, if you like, if you take this biological analogy. But probably something like 100 billion synapses. 100 million, I'm sorry, synapses. And the other thing of this is that it's a less known, perhaps, paper. Actually, it's also a famous paper by Turing. It's a chemical basis of morphogenesis, pattern formation. So the stripes on the zebrafish, actually, there is a certain there is a certain differential equation that Turing proposed, which actually describes formation of the patterns. So I'll stop here, and I'm happy to discuss.
Thank you very much. I'm going to give it to the microphone to the first, to the only official discussant. But just one question. Is this about, have you told us something about neural nets, or have you told us something about language?
I think both. I hope both. I think there is some sort of remarkable interaction between neural nets and language, is that language turns out to be simple enough that it can be picked up by this, you know, relatively simple statistical models. And neural nets turn to be sophisticated enough that they can actually pick that up. It's it's all very surprising, I feel.
Yeah,
well,
Richard, it's yours.
All right, thanks for a really interesting and thought-provoking talk. So lots of really cool ideas here. I actually just have, I have a comment, and then I have a few like basic questions I'd just like to get your thought on. I think they'd be enlightening for everyone too. So my comment would be, so you raised this question of what's like the physical law for language. What is it that allows us to generalize linguistic data? So you might be interested in checking out, so this has been basically the goal in generative linguistics and language science, to figure out what is the physical law for language. Most of the proposals people have come up with are not really compatible with neural networks. But there is a lot of really interesting work in information theoretic approaches to language, where you might find some hints. about like what a physical law for linguistic data might look like. And a lot of the ideas there are drawing from statistical physics. As for questions, it's interesting discussion questions. So it looks like the physical laws you're alluding to are not really only about language, because you're also finding that it's possible to learn things about images and so on from much less data than you might think. So like, what do you think the physical law actually is? What's like the deepest origin for that physical law? Why does natural data lie on a low dimensional manifold? Something beyond just simplicity. Like, what do you think is the most fundamental reason? It is maybe something arising from physics. And relatedly, I'd be really curious to know what you think about, like, again, what's the most fundamental reason for why we see double descent? Why is it you specifically see a spike in the test loss, usually one spike in the test loss followed by a decline? And yeah, I'm just very curious for your thoughts.
Yeah, thank you for thank you for the comments and the questions. It's this is really I think that's kind of a mystery because so it looks like now that roughly the same architectures which work for language, as you pointed out, work for vision and speech, all sort of even something like like protein folding maybe or some other stuff which seems unrelated on the surface. So it does suggest that there is some sort of physical.
Sorry, just a second. Could you take down your slides so we can see you better?
Let me unshare this.
Yeah, thanks.
How do I unshare? Oh, okay, perfect. Yeah, is this okay?
Yeah.
Yeah.
Okay. So yeah, so I think there is something pretty remarkable going on, which I personally, to me, I never thought it would be like the same model would work for like everything in the world. It's very strange. But that's what we observe. I mean, we have to accept reality. So that suggests that there must be some sort of fundamental physical reason that all the things kind of work, if not the same way, but like similarly enough that the same models can, pick them up, or very similar models can pick all those things up, which actually suggests that there is something probably we're fundamentally missing about like the physical laws. One way maybe you can kind of think that I sort of I'm not a big fan of the anthropic principle, but you can kind of think, okay, maybe we wouldn't be able to evolve in any other sort of universe in which these things would not be like relatively simple. This is like complete speculation, of course, but it's like 4 years ago, I would have dismissed it as like a purely unfounded speculation. But now it's kind of hard to dismiss it, given these remarkable successes. Yeah, so maybe something like that is happening. I think we need to get better understanding of what's possible with these models, and we don't know what their limits are, and we don't know like how much this can be pushed. For the okay, I'm kind of switching gears to a very different thing. So for double distant, I think it's quite interesting. The fact is, like, why do we have? So really, I think the way I think about it now, there are these really two regimes. There is this classical regime when you control carefully what they basically taught us in, classes and probably still teach. You carefully control complexity of the model, and if you do it correctly, you get good results. And this kind of laissez-faire modern world of deep learning, you just like throw as much parameters at it as you want, like throw all the compute in the world, and it works just fine. And it turns out, and now we kind of understand, at least in some cases, that mathematics of it for like linear regression and some simple models, we actually can prove that it's not clear which one is better. I mean, it's a subtle question, which one is better, but certainly in some cases, the overparameterized regime is better, and in other cases, the classical regime is better. You have to regularize and so on. And why there is only one peak? There could be several peaks. I think that there is only one peak in general because I think it has to do more with like the way the data usually are and so on. Certainly you can construct cases with multiple peaks artificially. So it's not a fundamental mathematical rule. It's just something about like the way that things usually work.
Do you think double descent fundamentally depends on things like using stochastic gradient descent or noise in the gradients or regularization?
No, these are not fundamental things. You can get it. So the cleanest way to get it is just using very simple linear regression with a random feature model. It's very simple. In fact, in some sense, it was observed like like 30 years ago. The curve was observed in some papers, which I think the difference now is that it is clear that this is a very general phenomenon, not some sort of artifact of a specific setup.
Thanks. Very interesting. We can open it up now.
It's everybody else's turn if you want it. Yeah, this was a remarkable talk, and there's a lot of things to talk about. And you're there out. I've given permission to talk to a lot of people out in the attendee list if you want to, unless you're absolutely stupefied by the surprise and you have nothing to say until you've had a chance to digest it. That's it. Some people are nodding.
Yeah,
if
digesting all of the stuff is hard. I'm still digesting.
We still have a few minutes. Was there anything that you were planning to show that you didn't show in the interest of time? For example, do you want to intimidate them with that mathematical one that you didn't present?
Well, I had a question.
Oh, okay. Go ahead.
Do I have a video? No video. Okay, never mind. I can't see anybody.
He'll do it 1 second. It'll be fixed.
Yeah, that was a great talk. I enjoyed that quite a bit. Coming from neural networks back in the 90s, one of the things that struck me is a lot of what you're talking about is regularization, and there's a sort of a confusing aspect of this back in the 90s. John Moody had done some work where he just looked at the partial derivatives of all the weights against the error, and he showed that essentially the neural network would keep a very small dimensional structure and then sort of expand. Oh, I'm getting more questions here.
What? I'm sorry, we were working on showing you. Was there another question elsewhere?
Well, can you hear me at all?
We hear you completely. We just haven't had a chance to show you.
Okay. Well, I can still talk to Misha, I suppose. So I don't know if you're familiar with that work that Moody had done, and basically showed that there was this sort of auto-regularization that was occurring. And these were, of course, simple neural networks. More recently, a group of statisticians, Martin Mahoney, published a paper where they looked at 100 different architectures, and they characterized the dynamics of the learning based on the eigenvalue distribution, showing that it started out as a random set and then slowly began to create some covariance structure and then finally collapsed as it finally learned. And the point that they were sort of making is that this regularization seems to pop out of almost nowhere. And I got a sense that you had this similar feeling that this high dimensionality is seemingly allowing for this regularization to happen. And yet we don't really have a good sense of what's going on here, unless I missed something you were saying. I fear you're in the same the same phase as everyone else here. Is that right?
I wouldn't say we completely have no idea. I mean, it is certainly very surprising, but I think we understand some aspects of it now. For example, for linear models, we understand pretty well Okay, what is maybe one shocking thing about this, like why are we writing papers about, this is year 2024, why are
Right.
we writing papers about linear models? That's what Gauss did.
Right.
Like 19
genre.
whatever 70 whatever 6 or something. I mean 1796. Not 9 70, yeah. It's like, and we're still like writing papers and we're finding things out about linear models. So it's kind of surprising. It brought up all of this, things that we turned out we don't understand very well. I think for linear models we have a pretty good understanding now of what is happening and where this. So we understand that, for example, that gradient descent on its own, SGD on its own, can do this regularization, and sort of we somewhat understand what happened in nonlinear models, but it's much less clear, like much. Yeah.
So were you familiar with the Moody work? This was 1991, of course, and there what was surprising is that in the 80s, of course, anyone could take a single layer neural network and apply it to a problem, and it kind of worked. And we all said, well, that's impossible because, there's too many parameters and they only had 10 data points. So how did they get this to work? And what appeared to be going on is that, again, the networks, probably through some kind of distributed computation or competition, would in fact start to regularize themselves. It's as though you think of a principal component or an eigenvector would come up, and then it would push the others down, but then some would be correlated, and there'd be this kind of free-for-all argument about who was dominating. The Mahoney results are much clearer in that they looked at hundreds of deep learning architectures, and they did a fairly comprehensive statistical analysis of the learning dynamics, and that's why it fits into your story somehow. But here they did all this empirical work, and they found these 5 distinct phases that I think are related to some of the stuff you were bringing up. Now, exactly why that happens, the underlying dynamics of these nonlinear large structures, you're right. Linear systems are better. Gaussian linear systems, that's what we should be studying. Stop all this nonsense with this complex nonlinear kernels we don't understand. That's and especially with 900 billion parameters. I don't get it. And it sounds like you have the same kind of chagrin that I have.
I would love to study the linear systems, right? But they just like you cannot build a like LLM out of them,
Right.
sadly.
Right.
But yeah, I'm a little familiar. I'm not familiar with Moody's work, but I'm familiar with Mahoney's work.
Okay.
And it certainly, we observe this. It's we are far from understanding these mechanisms, but it is clear they're doing dimensionality reduction. So I think the mechanism I discussed today, I believe it's a big part of what is happening in the things. Certainly for MLPs, I think it's clear. But even for that, if you want to analyze it mathematically, it's pretty tricky, even though it's a much simpler mechanism.
Yeah.
So we're still quite far, but I'm okay. I'm okay not understanding, like not proving every theorem about it. Like I really want to function like a physicist, like Newton didn't prove stuff about, or whatever. Physicists don't prove stuff about, laws of physics, right? They make observation and they posit mathematical, mathematical rules that describe this, and then they make derivations based on those.
Right. Well, yes, but this leaves us sort of at an impasse with regard to the large language models and what their mechanisms are. And as you point out, there's these autoregressive, the attention heads are autoregressive systems. And there was a recent theorem, I think about a month ago, I can't remember the author, that showed that with a sufficient number, whatever that is, 4 or 5 you start basically getting a recurrent neural network. So you're starting getting dynamical properties of the thing. So the underlying dynamics of this seems to me the place where a physicist would have perhaps the largest useful impact in trying to figure out what's going on. Otherwise, I think Yoshua Bengio's right. We're just sleepwalking through this. It's just a really horrible time, and we don't understand what's going on, and everyone's pretending like they do.
Okay.
Oh, I think it's a really exciting time, actually. This is like from my point of view, this is like the most excited I've ever been about, science.
Okay, and we're all grateful that not all the problems were solved today because we still have 9 days. Okay, Gary, one last one and a short one. Go ahead.
This is more of an observation than anything else. I noticed that nothing in your talk refers to the attention heads, which are, the one of the main features of transformers. So, do you have anything to say about them?
So not quite. That last slide I showed does extract this from attention.
Okay.
So you can okay. I don't have a lot to say about that, but you clearly can extract the same type of dimensionality reduction from this attention layers, and this clearly have you just get the semantic information pretty nicely.
Okay. Okay, done. By the way, we'll hear more about attention from Eli Pavlik on the very last day. So I want to thank you for coming, so to speak, and come back during other sessions, please, because I think your talk will resonate several times.
Thank you very much.
Thank you, Misha.
It's really great. Thank you.
Okay, you have a very short break, and people will be coming in for